Today we shall discuss Kirchhoff's laws. Before discussing Kirchhoff's laws, we could have used Ohm's law to analyze different electrical circuits. But Ohm's law is specifically used in situations where the circuit is not very complex, it does not include more batteries. The circuit can be easily broken up into series and parallel networks, but sometimes in complex circuits it is very difficult to analyze whether some resistances or capacitors are in series. There are many batteries connected across the circuit, and therefore Ohm's law cannot be used in a very simplified manner. In those situations, we use Kirchhoff's law. The Kirchhoff's law is based upon the current and the potential differences across different circuit elements, say for example capacitors or resistances or inductors. The currents and the potential differences across different circuit elements are analyzed, and on that basis we use Kirchhoff's law to simplify a complex network. And there are two such statements associated with Kirchhoff's law. The first is called as the junction rule or KCL, or simply you can say it is Kirchhoff's current law, which is abbreviated as KCL. Now this junction rule or KCL is nothing but it is just an illustration of the principle of conservation of charge. And this Kirchhoff's current law is related to a particular junction in an electric circuit, whereby a junction refers to any point where many electrical components get connected. So KCL states that the algebraic sum of currents meeting at a junction in a circuit is zero. The algebraic sum of currents meeting at a junction in a circuit is zero, which means that current might be entering the junction, the currents might be leaving the junction, but the algebraic sum of all those currents which are either meeting a junction or leaving a junction is zero. Let me take an example. Suppose there is a junction in a complex electrical network. Suppose there are one or more resistances that connect or that meet at that particular junction. Suppose in one of the resistances current flowing is I1, in another the current flowing is I2, in the other one the current flowing is I3, and suppose in this one the current flowing is I4. So the sum of currents meeting the junction is zero. So you can say that this law can be simply related as summation of I equal to 0. Now the convention that we have to apply is currents entering the junction. Suppose the junction is named as P. The currents entering the junction are taken as positive and currents leaving the junction are taken as negative. So in this situation I can write currents entering I1, I2 and I4. So they can be taken as positive. I1, I2 and I4 are taken as positive as they are entering the junction, and I3 is leaving the junction, so it should be taken as negative. So the sum of all the currents entering and leaving must be 0. This can also be written as I1 plus I2 plus I4 equal to I3. So again the statement can be expressed as sum of currents entering is equal to sum of currents leaving. So this is a very simple illustration of Kirchhoff's current law. In a complex electrical circuit, there might be several such junctions where we have to apply this principle, and this principle is nothing but it is the illustration of conservation of charge. So KCL simply illustrates conservation of charge, or you can say that it is based upon conservation of charge. Now the next law that we apply in complex electrical networks is the loop rule or KVL or Kirchhoff's voltage law. Now, in this case, we have to assume a closed network or a closed path or a closed loop in electrical circuit. There might be several such closed loops in a complex electrical network. In any closed loop of an electric circuit, the algebraic sum of the potential differences is zero. The algebraic sum of the potential differences is zero. It means that the potential differences occur whenever a current is passing through a resistance. There might be some battery or cell whose EMF is also to be taken into account for the potential differences. There might be capacitors. At the ends of the plates of the capacitor, we get a potential difference. So, whatever be the type of electrical component, we have to consider all the potential differences that might occur in the closed path of an electric circuit. But here we have to follow a basic convention. If the potential decreases, then it is taken as negative, and if the potential increases, then it is taken as positive. Now, potential increase or decrease has to be taken into account when we are moving along the closed loop. The sense of movement will allow us to associate loss in potential or gain in potential in the closed loop. So basically, suppose if there is a battery or a source of EMF in an electrical circuit, suppose AB represents a simple path in a closed loop, and suppose we are moving along the closed loop in such a direction that we are crossing the battery from the positive terminal to the negative terminal. That means if we are moving along the direction A to B, we are obviously moving from the positive terminal to the negative terminal, which means the potential drop. There is a potential drop. That means the potential is decreasing. In this case, the EMF of the battery is to be taken as negative. The EMF epsilon of the battery is to be taken as negative, because the potential is decreasing when we are moving from the positive to the negative terminal. Whereas if the opposite happens, while moving from A to B, we are definitely moving it from negative to positive potential. That means the potential is increasing. In this case, the battery EMF is to be taken as, battery EMF is to be taken as positive, because the potential is increased. The negative terminal is at low potential, the positive terminal is at high potential, and in this case it is from high to low, so EMF is negative. In this case we are moving from low to high, so it is definitely positive. Now, in some situation we might cross a resistance. So suppose we cross a resistance in the sense of the movement of the current. Then accordingly we have to use a sign convention for the potential difference across the resistance. Suppose this is a resistance R and a current I flows through it, and suppose we are moving from one end of the resistance to the other end in the sense from A to B. That means this is our direction of movement, A to B. Now we know that current flows from high potential to low potential. That means if we move in the sense from A to B, the potential is definitely decreasing because current is flowing from high to low potential. In this case, the product of I into R is obviously negative because we are moving in the direction of current. So if you move in the direction of current, that means the potential is decreasing. So product IR, which is the potential difference across the resistance, that has to be taken as negative. Because in Kirchhoff's second law, we have to calculate the algebraic sum of all the potential differences. Now, if the opposite happens, suppose a current I flows in this direction, and suppose we are moving from B to A in this sense, then obviously we know that current flows from high to low potential. We are now moving from low to high, which means that the potential is increasing. That means the potential difference IR should be taken as positive. It also means that if you are moving opposite to the direction of movement of current, then the product IR should be taken as positive. So this is to be analyzed in any closed path of an electrical circuit, and the sum of all those potential differences, including the battery EMF, including the product of I into R, if there is some capacitor, you have to consider Q by C, and so the algebraic sum of all these potential differences should be 0. Let us take an example to illustrate how to apply Kirchhoff's law. Before saying that, as I have already told that Kirchhoff's current law or KCL demonstrates the principle of conservation of charge, the Kirchhoff's voltage law or KVL demonstrates the principle of conservation of energy. So KCL is associated with conservation of charge and KVL with conservation of energy. So now we want to illustrate how to use KCL and KVL in this circuit. Suppose according to this circuit there are two cells of 4 volt and 3 volt, 2 volt. 4 volt having internal resistance 3 ohm and 2 volt having internal resistance 1 ohm, and they are connected with 5 ohm, 4 ohm and 6 ohm resistance. So we want to find the current flowing through the circuit. Suppose this battery or cell is capable of producing current I1 and this cell is capable of producing a current I2. Suppose through the 6 ohm resistance the current I3 flows. As I1 is delivered by the 4 volt battery, so definitely I1 will enter into it, and 2 volt battery delivers I2, so definitely I2 should flow into it. Now these are the currents that we want to calculate, and if possible we can also calculate the potential drops across the different resistance sources. So let us start with KCL and KVL. We can name the circuit so that it becomes easy for us to find a loop or a closed path or a mesh, whatever you say. Suppose this point is point A, point B, point C, point D, point E and point F. So there are 6 junctions A, B, C, D, E and F. Suppose at the point B or at the junction B, what happens if we use KCL? So by applying KCL at junction B, obviously you can see that I2 enters the junction, I1 enters the junction, I3 leaves the junction. By Kirchhoff's first law or KCL, sum of currents entering the junction is 0, the algebraic sum is 0. So for currents entering we take positive, and for current leaving, that is I3, we take it as negative, and this sum is 0, which means that I3 is obviously I1 plus I2. This is our first equation. Now let us apply KVL or Kirchhoff's second law in any closed path. Let me apply KVL in this closed path. Suppose in a clockwise manner, let me apply this KVL. So this may be called as loop 1, or you can also call it as AFEBA, and we are moving in the clockwise manner. What happens if we move in the clockwise manner? Now I am moving in this direction, so I am moving from plus to minus of the battery. That means there is a decrease in potential, so this should be taken as minus 4. Plus to minus, the potential decreases in this direction, it is minus 4. Now you see that current I1 moves in the opposite direction and I am moving in this direction. So definitely current into resistance, this potential difference should be taken as positive. So this will be 3I1. In this direction we are moving opposite to the direction of current. So again 4I1 will be positive. Now we are moving in this direction. We are again moving opposite to I3. So this will be 6I3. Then we come back in this sense to close the loop. So definitely we are moving opposite to I1. So again 5I1 should be taken as positive. Now you already know that I3 is I1 plus I2. So this is 3I1 plus 4I1. 3I1 plus 4I1 plus 5I1. 12I1 plus 6 times of I1 plus I2 is equal to 4. So this is 12I1 plus 6I1 is 18I1 plus 6I2 is equal to 4. We can take 2 common. So 2 9s are 18, that is 9I1 plus 3I2 must be equal to 2. Dividing throughout by 2, you can say this will be the equation 2. Now let me apply KVL in another loop. Suppose in this loop, let me now follow anti-clockwise manner. This is loop 2. Let me move in an anti-clockwise manner. Clockwise or anti-clockwise, this is purely a choice. You can do anything, but I have to apply the proper convention only. So let me move in this direction in loop 2. So loop 2 will be B, C, D, E, B. Now we are moving in this sense. That means we are again moving opposite to the direction of the current. So 6I3 is again positive. In this sense, this is 5I2 which is again positive. I am moving from the plus to the minus terminal of the battery. That means potential is decreasing, so it will be minus 2. Again moving opposite to the direction of I2. That means 2I1, R1 into I2 is obviously positive. Again in this sense it is 4I2 which is also positive. That means the sum is 0. The sum of potential differences should be 0. So again 5I2 plus I2, 6I2, 10I2. So 6 instead of I3 we will write I1 plus I2. Plus what we get is 5 plus 1, 6 plus 4, 10I2 is equal to minus 2 goes to the other end, that is 2. So this is 6I1 plus 6I2 plus 10I2, that is 16I2 equal to 2. Dividing throughout by 2, we have 3I1 plus 8I2 equal to 1. This is the third equation. Now we have to solve these two equations 2 and 3 and find I1 and I2, so that we can also find the current delivered by each of the battery. We can also find the current flowing through the 6 ohm and the potential differences across each resistance, that also can be determined if we can find I1, I2 and I3. So these two equations will be used to find I1, I2 and I3. So you can note it down and then I will use these two equations only. So our first equation is 9I1 plus 3I2 is 2, and second equation is 3I1 plus 8I2 is equal to 1. So now we can multiply the first equation, this equation 2, by 3 and the second equation by 9. So therefore what we have is 3 into 9 is 27I1 plus 3 into 3 is 9I2, 6. Second equation multiplied by 9, 27I1, 72I2 is equal to 9. So therefore if I subtract the second equation from the first, or the first equation from the second, suppose this equation is 2a and this is 3a and and if I subtract 2a from 3a, then what I get is 27. I will cancel out. 72 minus 9 must be equal to 9 minus 6, that is 3. So this is 63 I2, which means that I2 is 3 by 63, which is 1 upon 21 ampere. Now, if I substitute in any of the equations, I will get I1. So let me substitute in the third equation. Let us substitute in this equation. This is 3I1 plus 8 into 1 upon 21 is equal to 1. So this is 3I1 equal to 1 minus 8 by 21, which means 3I1 is 21 minus 8. Is 21 minus 8 is 13. So I1 will be 13 divided by 21 into 3. So this will be 363 ampere, 13 upon 63 ampere. So therefore, you can always now you can find I3, which is I3 is equal to I1 plus I2. You can now see that I1 is 1 by 21, which we can also write 3 by 63, and I1 is 13 by 63 and I2 is 3 by 63 or 1 by 21. So if we add them, that is 13 by 63 plus 3 by 63. So this will become 16 by 63 ampere. 16 by 63 is approximately 0.25 ampere. And now, after knowing all the currents, we can easily calculate the potential differences across each of the resistances. Because the resistance value is known, we know the current flowing through them. Current into resistance is the potential difference. If we want to find the terminal potential difference across each of the battery, that we can also do. Because terminal potential difference is EMF minus current into internal resistance. We have I1 and I2 flowing through the internal resistance. So terminal potential difference is simply 4 volt minus I1 into 3, which you can easily calculate, and so on. So this is a way of applying Kirchhoff's law to complex electrical networks. Let us discuss two more problems on Kirchhoff's law. Now the first problem is two cells of EMF E but different internal resistances R1 and R2 are connected in series with an external resistance capital R. So this is the first cell having EMF small e and internal resistance small r1, whereas the next cell is also of EMF E and internal resistance is R2 and the external resistance is capital R. We have to find R provided the potential drop across the first cell is 0. This is the given condition in the question, that the potential drop across the first cell is 0. Now here we can apply Kirchhoff's law. So we have to find the current flowing through the circuit, and with the help of that and the given condition we can definitely find capital R. In this problem it might appear difficult to identify the direction of current, because the first cell will deliver some current, the second cell will also deliver some current. Now the direction of current will obviously from the positive terminal of each of the cells. So where will the current meet? It might be very difficult to predict. So in these situations, in the entire loop, we assume that there is some current flowing. So we don't enumerate currents differently for different cells, but in such cases where it might be difficult to identify the direction of the current, throughout the loop we assume there is a current which is flowing. So in this situation, let me assume that there is a current I flowing. So this is the positive terminal and this is the negative terminal, and suppose we assume that a current flows in the circuit in this manner. In this manner means anti-clockwise. Suppose a current I flows in the anti-clockwise sense, in the interloop. So let us apply KVL, Kirchhoff's voltage law, in this loop in the same sense as the current is flowing. So that means we are trying to trace the loop in the anti-clockwise sense. What happens if we do so? So we are moving in this direction. So that means when we are moving in this direction, we are actually moving in the direction of the current, because the current is also flowing in the anti-clockwise direction. So therefore, current into resistance is definitely negative. In this direction, if we trace the second cell, we are going from negative towards the positive terminal of the cell. That means the potential is increasing, so it will be plus E. Similarly, for this cell, we are also going in the direction of the current. So current into internal resistance is negative, and from the negative to the positive terminal, this will be the direction. So we are going in the direction of increasing potential. So again, E is positive. And by KVL, the sum of potential differences must be 0. From this, we can say that, I forgot to calculate R. So again, current is also flowing through R, but in the same direction. Current is flowing through R in the anti-clockwise sense. So current into resistance is again negative. Remember that if we move in the direction of the current, current into resistance is negative. So minus IR. This must be equal to 0. So from this you can easily see that if you take I common and take to the other side of the equation, 2E will become I times of R1 plus R2 plus capital R. Now again, let us go to the condition that potential drop across the first cell is 0. So since the potential drop across the first cell is 0, we can write E minus I R1 is 0. Potential drop across the cell is equal to EMF minus current into internal resistance, which is 0 by the given condition. This obviously means that I equal to E by R1. So if you put the value of I equal to E by R1 in this equation, what we get is 2E equal to, instead of I will write E by R1, R1 plus R2 plus R. So definitely you see that E cancels out, this becomes 2R1 is equal to R1 plus R2 plus R, which means that R is equal to 2R1 minus R1 is R1 minus R. So R is R1 minus R2. So this is how we apply KVL in these situations. Let us move on to the second question. Now in case of certain electrical networks where it is required to find the equivalent resistance, sometimes it might be difficult to analyze the circuit on the basis of series and parallel. So in those situations also we can use Kirchhoff's laws to find the equivalent resistance. So this is a cube in which you have to calculate RAG, means the equivalent resistance between the points A and G. That means diagonally opposite corners of the cube, and each side of the cube contains a resistance, and that resistance is capital R. So this is what we have to find. We have to find RAG if each resistance is capital R. So each of these resistances shown in the diagram is capital R, and we have to find the equivalent distance between the points A and G, the diagonally opposite corners. The same result you will get if we apply against points E and C or B and H. We will get the same result, but as per this diagram, it is required to find the equivalent resistance between the points A and G. So in this situation, we will try to apply Kirchhoff's law. So between the points where it is required to find the equivalent resistance, we assume that there is a battery connected. So between points A and G, let me assume that there is a battery which is being connected. Let me assume that the battery is an ideal battery, it has no internal resistance, and its EMF is suppose V volt. So there is a battery of battery of EMF V volt connected across points A and G. This V volt battery will definitely deliver a current. Now, if you look at the symmetry of the problem, the current is entering at the point B, and the current is leaving the point G. Obviously, some current will enter at the point B and some current will enter at the point A and some current will leave the point G. Now this current that is entering at the point A is branching into three different directions. This direction and this direction. And all the resistances are of same value, that is capital R. So symmetrically, the current entering this one, this direction and this direction, that means along AB, AE and AD will be definitely equal because the resistance is, each resistance is capital R. So let me assume that a current 6I is delivered by the battery, and so current flowing through this arm is 2I and 2I, because the current distributes in a symmetric manner, because the symmetry of the circuit is such. So definitely at this point also 6I should enter into the battery. That means in this arm it is 2I, along this arm it is 2I, and along this arm also it is 2I. Now again you can see that 2I now branches in this direction, that is BF and BC. So this must be I and this must be I. And for this one also 2I will branch in this direction and in this direction. So this will be again 2I, I and I each. So that means current 2I that enters here will also again branch into I and I respectively. So I plus I 2I, here I plus I 2I, and in this direction I plus I is 2I is flowing. So the symmetry, from the symmetry it is what we get. This 2I is this one. So now let me assume that let equivalent resistance between A and G, that is RAG, is X ohm. So therefore, by Ohm's law we can write potential difference is current into resistance. So potential difference between A and G is obviously the battery EMF, that is V. The current delivered is 6I. So V equal to current into resistance. Resistance we have assumed between A and G is X ohm. So this is 6I into X, which means that the current I is V by 6X. Now let us apply KVL in any of the loop. Let me apply KVL along this direction, A, E, H, G, back to A. So this is the direction of the loop from A, E, H, G, back to A. So this is the direction that I am moving. So let me apply KVL along A, E, H, G, back to A. Let me call this path as V, though V refers to the battery EMF, but still I am just trying to enumerate the loop. That's why I am naming it as V. A, E, H, G, V, A. So in this direction, if I apply KVL, I am moving in the direction of the current. So I have to take current into resistance as positive. So 2I into R is, current into resistance is negative. It is minus 2I into R. In this arm it is minus I into R. In this arm it is minus 2I into R. And then the EMF is from the negative to the positive, so it will be plus V, and all the potential differences must be equal to 0. The sum of the potential differences must be equal to 0. Again you can see it, 2I into R, I into R and 2I into R, these are all negative and V is positive, sum is 0, which means that V equal to 2I plus I plus 2I, 5IR. Now when I substitute the value of I in this case, what I get is this equation and this equation. So V equal to 5IR implies V equal to 5 into, instead of I will write V by 6x into R. So V will cancel out. You will get 6x is 5R, which means x is 5 by 6 times of capital R. So this is the resistance or the equivalent resistance between the points A and G. So therefore what we can write is the resistance, equivalent resistance between the points A and G is 5R by 6. So this is a simple way of applying Kirchhoff's law to find the equivalent resistance between any two points in a complex electrical network.